Welcome everybody. The subject of today's webinar is space materials. I'm Gabriela Opiła. I'm a PhD student at AGH University of Krakow, and my main interest is physics during my research. But I think that today's presentation will have kind of more broader topic, because I'll talk about subjects that are connected to geology and chemistry, maybe material engineering a little bit, maybe a tiny little bit of history and archaeology as well. So I hope that there is something interesting for everyone. And the choice of this subject was also a little bit connected to the fact that Space Technology Center of AGH University opened a new building recently. And this building also has a space materials laboratory. But I think I'll go a bit broader than typical laboratory research in what I'm going to talk about today. So yeah, what do we understand by space materials? I think the first division would be to say that those are materials from space and materials that were designed for use in space. Of course, there are also materials that were designed just as materials and are also used in space, but I would still put them into this category of materials for use in space, but still manufactured in terrestrial conditions. And when it comes to materials from space, we can talk about meteorites, also asteroid samples, samples from other planets, comet samples, and all those carry important information on space resources, on the conditions on those other bodies. They are also, at least meteorites, are most available samples of extraterrestrial matter. There are also types of space materials that we could consider space resources, because not only do they carry information about their parent bodies, but they also can be used in potentially industrial way. Such space resources are, for example, regolith, which is probably the most talked about space resource, I think I could say. For those that don't know, regolith is a sort of dust that covers the surface of the moon, of other planets, of comets. There is also regolith covering the surface of some places on Earth as well, because it's tiny dust particles that are created as a result of certain processes. And the difference between regolith and like earth, like ground, like something that in Polish we would call ziemia or gleba, between soil and regolith, is that regolith is created without organic processes, while soil, or in Polish gleba or ziemia, contains those organic matter, organic particles. Also, various metals and minerals can be found outside of Earth, and some rocks have trapped gases, water, other important substances. Also, from regolith, some gases or metals can be extracted. And regarding materials designed for use in space, of course, in order to have use for any other types of space materials, we need to first have a spacecraft. So those materials would be, for example, some super alloys with superior properties that can withstand extreme conditions. But also, in order to study other materials using manned missions, it's important to have materials for medicine, such as for diagnostics, for therapy, maybe regenerative medicine, because long-term missions must be ready for anything that could happen. And also sensors and constructions technology need to rely on materials that also are resistant to conditions in space, because sometimes it's enough if a sensor works for a very short time, and sometimes it's like, for example, there are spacecrafts like the Voyagers that can work for years and for decades. So we need really, really durable technologies. And regarding the first usage of space materials, I would like to start with meteoritic metal, because while meteorites are currently mostly collected by either researchers or people who like pretty rocks, so just collectors, or are studied by scientists. In the past, the meteoritic iron was the first type of iron that was available for use, because it didn't require ore processing abilities. It didn't require as high temperatures as iron ore would require. So even in Bronze Age, so before Iron Age, there were objects manufactured from meteoritic iron. The examples of such objects include dagger of Pharaoh Tutankhamun from late Bronze Age, which was likely gifted to Tutankhamun's grandfather, and it was quite thoroughly studied, so it is confirmed that indeed its origin, its material is meteoritic iron. There was also this dagger, which is even older, but unfortunately it corroded, so it wasn't possible to obtain as precise information on it, but it's the first dagger of this metal that is known. And while those daggers were probably not really tools for war or for fighting, there are also even more practical objects made from meteoritic iron, because this arrowhead found in Switzerland was also confirmed to be made of meteoritic metal. So even hunting could make use of material that came from space. And there is also a so-called Iron Man, a Buddhist statue, that is confirmed to be carved from Chinga meteorite. Unfortunately, it is still unknown when it was carved, because in the case of the history of it is not really well known, and only recently it was identified as actually being made from this meteorite. So also space materials can help with decorative, maybe ritual objects. And whatever information can we get from meteorites from a more practical point of view? Meteorites have, in most cases, magnetic properties. And in some cases, not all, maybe in rare cases, the history of magnetic fields can be recorded in meteorites. In more cases, history of the solar system can also be recorded in meteorites, due to the fact that the specific type of melting could have occurred, which causes, for example, the grains of various minerals in meteorites to be distorted in certain ways. Also, which is probably a little bit more obvious, we can identify what minerals are present on other celestial bodies thanks to identifying them in meteorites. And what I think currently is particularly exciting for the researchers is that meteorites can carry information on origin of life, because on some meteorites, traces of organic substances have been found. And some scientists theorize that maybe even meteorites could have carried to the Earth the necessary compounds for the origins of life. And here is a brief example of what can be studied in the context of a meteorite, because a team that I am part of conducted a study of mineral and elemental content in a chondrite, Northwest Africa 869 meteorite, and we wanted to determine the composition and properties of the studied meteorite sample. Here is this sample. We can see those various minerals present in it. We can see the fusion crust, this bit leathery brown structure on its surface, and also a thin plate of this meteorite. A little bit of this meteorite was also powdered in order to study its properties. And here is a high-resolution image of an iron nickel grain in this meteorite, along with the abundances of those two metals, and identifying kamacite and taenite, which are the two crystallic forms of iron, also tells us quite a lot about history of such meteorite, because as I said, metallic iron usually doesn't naturally occur on Earth. And here we can see that a lot of a very big part of the surface of this meteorite contains iron in some form, but only in those parts where there is both iron and nickel, it's metallic iron. There are also iron sulfides, but in meteorites we can also find aluminum, titanium, so other metals can also be found in extraterrestrial matter. We also performed a study of X-ray diffraction, thanks to which we identified other minerals. And this power study can also allow us to identify phases in such a sample. Next, we have asteroid samples. And while it's not as easy to obtain an asteroid sample as a meteorite sample, well, for meteorite sample, of course, it also doesn't have to be easy. Like, you can go to a shop and buy a sample of a meteorite, but someone must have found that meteorite earlier. So there are whole expeditions sometimes to find them. But to get a sample from asteroid and to not have that sample undergone atmospheric pressure, have been melted by the atmosphere like meteorite sample. So to have a pristine asteroid sample, it is necessary to organize a mission. And there was, for example, a mission to Bennu, Ryugu, to get this kind of a sample. And then it is possible to determine mechanical properties of asteroid dust, so also that regolith. It is possible to find water-bearing clay minerals, which actually were found in a recently studied sample brought from an asteroid by an NASA mission. And by studying pristine asteroid samples, it is possible to explain the abundance of meteorite types. What do I mean by that? There are various types of asteroids, and there are various types of meteorites. I won't really get into that classification now, but what I would like to say is that the number of what types of meteorites we find on Earth doesn't match with the abundance of asteroids of that type. And why that might be? Well, obtaining that asteroid sample allowed people to understand that the matter from that type of asteroids, from which meteorites called C chondrites, so carbon chondrites, come, are quite prone to being destroyed in earthly conditions. So they would be very quickly would undergo weathering and probably turn also to dust. So that's why not as many C chondrites are found. And here is a picture of a tiny fraction of that asteroid called Bennu that was returned by NASA's OSIRIS-REx mission. We have microscopy images, and we also have a top-down view of one of the containers containing rocks and dust from this asteroid. We can also see a scale in centimeters. So we have this macroscopic view and this microscopic view. The images are progressively zoomed in. And one of those interesting findings is this sample is that some phosphate was found thanks to scanning electron microscopy. And phosphate is a natural source of phosphorus. And it's an element that provides a quarter of all the nutrients that plants need for their growth and development. It is also an important electrolyte in human body. So regarding research on astrobiology, asteroid study can bring really important answers. When it comes to samples from other planets, situation can get a bit complicated because, as I mentioned, meteorites, it is possible to conduct a very, very thorough research. When it comes to asteroid samples, well, the mission has been conducted, the samples were returned safely, some research has been made. When it comes to samples from planets, from Mars, we have meteorites. When it comes to Mars, there is also on-site investigation. There are Mars rovers, not one, multiple. But when it comes to Venus, so far, none meteorites from Venus were discovered. And it is actually estimated to be extremely rare and improbable that meteorites come from Venus to Earth for multiple reasons, actually. One of those being the orbits of those planets, gravitational fields, and also the properties of Venusian atmosphere, because such Venusian meteorite would have to first survive passing through Venusian atmosphere, which is very hot, extremely dense, and generally unfriendly to basically anything. But Martian meteorites allowed us to find evidence of organic compounds, for example, polycyclic aromatic hydrocarbons. And the Martian meteorites can also be considered as kind of chronicles of impacts experienced by Mars. Chronology can be established thanks to cosmic ray exposure ages, and some Martian meteorites even carry evidence of water, which was later than meteorite research studied, confirmed by on-site investigation. And on-site investigation of Martian environment informs about the impact of Martian conditions of minerals. For example, such a mission confirmed that apatite is constantly altered by radiation on the surface of Mars, because Martian atmosphere, in contrast to Venusian atmosphere, is less dense than Earth atmosphere. And so when it comes to Venus, it is not a trivial task to plan on-site investigation, because again, we come back to those extremely harsh conditions. So while there are some on-site Venus missions, they mostly perform atmospheric measurements, and sending expensive equipment, for example, spectroscopy, etc., would likely end up in destruction of that equipment really fast. So one of the challenges could be to design a material that could withstand those Venusian conditions. There are also planned, from what I saw on various space agencies' web pages, several sample return missions. Not in most recent years, but probably in 2030s, 2040s. Both NASA and ESA and Chinese Space Agency would like to have sample return missions, which would allow for much more precise investigation of the properties of Martian soil and Martian rocks and Venusian soil, because the professional equipment in laboratories could be used to study them. And while some Martian meteorites are confirmed, studying matter that coming from Mars could help confirm, in the case of other rocks, other meteorites, whether they are meteorites for sure. But I think we must wait for those sample return missions, maybe wait and see. And now let's go on to regolith. I've already introduced regolith as this kind of weathered upper part of rock on various celestial bodies and also on Earth. And most research that is shown here was done on regolith simulants, because fortunately the properties of regolith are in quite a lot of ways are reproducible in a laboratory. So it allowed people to have some ideas on how regolith can be used and processed. And not only this way, the studies of regolith that was brought, for example, by Apollo missions, they can enable people to create more accurate regolith simulants and plan actually applications of regolith. And here we have examples of, for example, molten regolith electrolysis. And in this process, oxygen is obtained and also this metallic substance. So such a process would be quite beneficial on space bases during space missions, because oxygen is necessary, is absolutely necessary for people to function, but also various equipment pieces can be made using metals. When it comes to construction applications of regolith, there are various ideas for regolith sintering, also called regolith sintering, both in vacuum and in the condition with atmosphere. And some researchers also reproduced with success such regolith structures. And there are ideas on so kind of composites using regolith and superalloys. Superalloys are another topic, but they are type of alloys that can withstand temperatures that are a higher fraction of their melting point temperature. So they are really durable, they are resistant to temperature, and many types of spacecraft use this kind of alloy. So the idea of the researchers that conducted this study is that in the future there will be remnants of spacecrafts that came to a planet and they would contain superalloys. So why would those superalloys be scrapped if they can be processed and used again to make something? And that something could take advantage of a superalloy and take advantage of regolith that is abundant. So in this way, there would be advantages of both regolith, which is abundant in that place, and of superalloys and their wonderful properties. And here is an example of what metals, what elements can be found on Mars, on other celestial bodies. And for example, in Martian meteorites, magnesium, aluminium, titanium, iron, and chromium are relatively common. And all of them are quite useful in nowadays technology. But there are also trace elements of lithium, cobalt, nickel, copper, zinc, niobium, molybdenum, titanium, and even rare earth elements such as europium. And some of them are also pillars of current industry. For example, lithium batteries. So really, there are resources that could serve for in situ space resources usage. But how can those substances be extracted? One of the ways is what I mentioned, molten regolith electrolysis, which allows to obtain metal and oxygen. Other technologies that are required to take advantage of space resources are drilling, but that space drilling must also take into account conditions in space, so microgravity, very, very low pressure, maybe even vacuum or near vacuum. There are ideas for asteroid mining for precious metals. There are also even ideas, some ideas are that they could be used there in space, some that they could be brought to Earth. And also a very, very precious gas is helium-3, and it could be extracted from lunar regolith. And here are pictures from a work about lunar helium-3 mining concepts. And the soil samples brought by the Apollo mission show what gases are released in which temperature. So here is the idea where excavator would get the regolith. The regolith would be transported using belt conveyors and then screw conveyors, and it would have to be transported to a heater, then separated using such an electrostatic separator. And I mentioned the idea of in situ space resources utilization. In situ, so in a place, without transporting, for example, from Mars to Earth or from Moon to Mars, just building processing facilities in a place where resources are needed. Because if a lunar base was to be constructed, or if a Martian base was to be constructed, it wouldn't be able to allow itself to wait for precious materials from resources to be transported from Earth. Also, transporting large amounts of mass would be actually expensive. So both for self-sufficiency and for cost effectiveness and for sustainability, it is important to consider in situ space resources utilization. Also, for such a base, it would be safer to be able to produce as much as possible in situ. And it would even lead to development of new technologies allowing for more effective processing of those resources. And I looked at what NASA focuses on in the context of ISRU. This is the abbreviation of in situ space resources utilization technology. And for NASA, the crucial aspects are regolith-based volatile resource acquisition and processing. Volatile, so those are these gases that I mentioned present in regolith. That could be helium-3, could be oxygen, etc. Also, regolith-based in-space manufacturing and construction. So, for example, bases made from regolith, like buildings, houses, factories, and Mars atmosphere-based resource acquisition and processing. And ESA also pays attention to the idea of using technology able to turn indigenous material into oxygen and water, which are considered to be critical resources for sustaining future human operations in deep space. So let's focus on requirements towards space materials. Hardware exposed to space must withstand all aspects of the space environment. First of all, when it passes through space, it can encounter vacuum. But also there will be thermal cycling later, because if it enters any kind of atmosphere, there would be interaction with it. And also the engine heats during its usage. So not only very low temperatures and very low temperatures, but also fast temperature changes are sort of a danger. There is also charged particle radiation, because outside of Earth's magnetic field, we don't have as much protection against cosmic radiation as we have here. There's also ultraviolet radiation and various types of radiation, more that charged particle radiation, but radiation can damage electronics. So electronics must be designed in such a way that it's either resistant to radiation or some shielding must be implemented. So also good material for shielding must be chosen, because in earthly conditions, usually quite heavy materials are used for anti-radiation shielding, and using heavy materials in a space is absolutely not cost effective. So shielding using, for example, water is implemented on the ISS, and in space bases, maybe regolith could help in shielding against radiation, like a thick regolith walls, basically. Also, plasmatics and atomic oxygen can endanger equipment in space and lead to oxidation. When it comes to habitable environments, flammability is an enormous concern. Such environments must also be, well, there must be odor proof when people are supposed to function there. They must be protected against upward time propagation. And then we also come back to resistance to erosion, resistance to corrosion, and to the strength to weight ratio. Regarding materials for spacecrafts, I mentioned before the possibility of using regolith along with superalloys, and the best known superalloy is called Inconel. Its history dates back to 1935. So it first was used in aerospace industry, which naturally spread into space industry. There are various subtypes of this inconel alloy. There are various niobium superalloys as well, superalloys based on cobalt, and also a quite new one, NASA alloy GRX 810, which is an oxide dispersion strengthened alloy. And here we can see a high resolution characterization of its microstructure. So there are scanning electron microscopy images of this superalloy. So we can see that there are those nodes here. Another way of finding materials that are resistant is using composites. For example, ceramic matrix fiber composites, braided composites, and polymer nanocomposites. And here is also a picture of GRX superalloy, and it was oxidized and in various temperatures. So that's some of the factors that must be considered in designing the superalloys. Another aspect that must be developed is materials for space medicine and for biomedical research. And that should include drug delivery systems, because while, for example, International Space Station is equipped with some drugs, it's still a tiny fraction of types of drugs that are available on Earth. And in space, human body might react a little bit differently, sometimes a little bit, sometimes even more than a little bit differently than on Earth. So both drugs themselves and delivery systems must be designed in a way that, for example, enhances absorption of the drug. Also, regenerative medicine must be taken into account, such as hydrogels including, for example, nanoparticles. For example, magnetic nanoparticles in hydrogel can stimulate bone regrowth, because in space, astronauts wouldn't have such an easy access to operational room. So it's important that if anything happens, they get well quick. There are also ideas for some compounds that would help with radiation protection, and if not against radiation itself, then against the consequences of exposure to radiation. Then there is the 3D printing for devices and even tissues, which again circles us back to regenerative medicine. Also, sensor and lab-on-a-chip technologies, which are important not only to study matter found on other planets, but also to study reactions of human body to extraterrestrial conditions. Then there are various nanomaterials and drugs that would mediate side effects of microgravity. Also, for space usage, materials for sensors should be designed. One of the examples of materials that are quite promising for sensors are MXINs, but also sensors can take advantage of quantum dots, carbon dots, multiple polymers are extremely useful in designing sensors, and also connecting polymer noble metal nanoparticle nanocomposites. And it can be used both in research and in monitoring health of astronauts. Here is an example of such a nanocomposite with nanoparticles for electrochemical sensing applications. And circling back to construction, apart from regolith itself and processed regolith, so sinter, cold sinter, etc., there could be technologies such as basalt casting and lunarcrete and astrocrete. And the idea of lunarcrete and astrocrete is that regolith, along with some biological substances, in this case albumin from human blood, would create composites with desirable properties, and it then could be transformed into something that kind of resembles concrete, hence the name lunarcrete or astrocrete. So, to conclude, a large variety of materials is needed to ensure safety and efficiency of space exploration, and humanity used to take advantage of materials coming from space at least since Bronze Age. This is the earliest that we know of. Maybe it was earlier, we don't know, but that's what was found so far. And materials coming from space are an excellent source of information on history of the solar system and extraterrestrial conditions. And also a quest for better material properties for use in space can be a motor of progress, because it can motivate us physicists, it can motivate chemists and material engineers to invent something even better than what is already known. So with this conclusion, thank you so much for your attention. It was nice to be able to talk to you about this fascinating subject.